Lecture 17 of Advanced Inference and Graphical Models. And of course, the first thing I'd like to say to everybody is Happy Thanksgiving. I hope that this is a very important holiday here at the University of Washington. And I hope that everybody has a nice break or whatever it is that you do for Thanksgiving or not. So you should read Chapter 5. You should have read Chapter 5. And in fact, you should also, by the way, start reading. If not, you should probably start reading Chapter 7. So let me add that as to the reading list. We're not going to really talk about the stuff that's in Chapter 6. And then the other thing I wanted to mention is that there are a couple of really good papers that are mostly by Tom Minka, who was probably the primary developer of expectation propagation. There's one paper entitled Divergence Measures and Message Passing, which is actually a really nice paper that talks about a variety of generalizations of Kullback-Leibler divergence and how one can see message passing and generalized message passing and generalized belief propagation and expectation propagation all sort of within the same light in terms of projections based on doing a minimization over a Kullback-Leibler divergence. And then there's also another paper of that same ilk around the same time, Structured Region Graphs, Morphing EP into GBP. And so there's a UAI paper from 2005 and actually an longer archive paper, I think from 2012, by the same authors in the same title. Okay, and as a reminder to everybody, you have an assignment due tonight, actually, or maybe you've done it already, at 11:45 p.m. electronically, which is your final project update. And I've commented on all of your final projects. For those of you who have, I hope to see those of you who some of the projects I've had some issues with, so I hope to see them corrected by tonight. And others of you are doing swimmingly on your final projects, and just need to continue on with what you're doing. Okay, so today what we're going to do is talk about expectation propagation, sort of finish expectation propagation, and then talk about mean field. Okay. So let's do a little bit of review. So remember, we have this exponential family model, which has a set of D statistics. And what we do in expectation propagation is break the statistics into two pieces. The first piece are what are called the tractable ones, of which there are dt of them. And the other, notice the typo here, the intractable ones here. So I have to fix that guy. There's intractable ones, and which there are di. So basically, we break them we partition them. The tractable ones have this index, phi of 1 through phi of lowercase phis, and the intractable ones have the uppercase phis. And again, it's typically the case that the lowercase phis produce a scalar value, whereas the uppercase phis might produce a vector value. Yeah, question?
Okay, so we talked about that the intractable components individually may be tractable, but as an aggregate, they become...
Yeah, individually they are tractable. It's only once they're aggregated and considered all together within the same model does it become intractable.
So how do we decide what is tractable and intractable? So basically, each of them can individually be tractable, but still we are separating them into...
Right.
Tractable and intractable.
That's right. That's right. So, I mean, this is the, as we talked about a little bit last time, this is the user's decision. So, you might have a computational limit or a computational budget that you must abide by. And maybe your computational budget is such that you can't do anything more expensive than a tree. The idea, again, is that the tractable components are sort of meant to be such that you can do them exact. You can do exact inference on the tractable component. So if you had an exponential family model that only had the statistics corresponding to the tractable ones here, and sort of essentially the uppercase phi guys were just gone, they were missing, then the assumption is that you could be able to do exact inference on that model. Now, the statistics are the things that determine the tree width of the model, right? So you might have, if it's say a regular graphical model, you might have statistics corresponding to the individual nodes, and you might have statistics corresponding to edges. Now, as you know, even if you just have a graph with edges, the tree width can be as large as order n. It can be as large as the number of variables if it's a clique. But what one might do is sort of have some of the tractable ones. I mean, the tractable ones might be one such that everything's independent. That's one example that we talked about. Or it could be the tractable ones correspond to a tree, which means that you're allowed to do no more than r squared computation in terms of r, which is the number of possible random variable values. Or you might have a k-tree as well, where you could, you might decide a budget, and maybe r is small enough such that you can afford to do r to the k plus 1 computation on a bundle of nodes. And you decide. So you have to decide based on your computational budget. So the examples that we're going to talk about are, in one case, where the tractable component just corresponds to the singleton, the unaries, and then the intractable one corresponds to all edges. And so in that case, whenever we add one edge to the set of unaries, it's basically like you have think of it as like a grid graph, but with one edge. And that's a tree. Everything's independent except for one edge, which is also going to be a tree. So that's a super simple tree. Right? It's obviously possible to compute marginals for that thing. But you can do more complicated ones, like you could have multiple edges, multiple disconnected edges. That would also be a tree. Or you could have you connect the edges in such a way that there are no cycles. That would be a tree. So in all of those cases, that's considered tractable. But we're talking, I mean, it's not like it decides it for you. The algorithm does it decide it for you. So in some sense, this is like a class of algorithms that, as we saw last time, generalize the beta free energy approach, and also generalizes loopy belief propagation. Because loopy belief propagation doesn't really give you much flexibility. It just sort of says, send messages around the edges in the graph. That's it, right? I mean, maybe you have an order of messages that you send. And so there's sort of a flexibility there. But there isn't a flexibility in terms of the manner or the structure of the messages. And it's either loopy belief propagation on the one hand or junction tree on the other hand. And there's a big gap in between. And so many of these methods are meant to fill this gap between just running belief propagation on a graph with loops and fully triangulating the model and doing a junction tree algorithm. I mean, there is a lot of stuff in between. And as you probably would hope, and as people see when they run these things empirically, that as one moves along this gap from loopy belief propagation to junction tree, the computational expense goes higher, but also does the accuracy. The accuracy gets better until, if you're willing to spend the exponential time, you get perfect accuracy getting back to the junction tree. But then there's not one single path between these two extremes, loopy belief propagation and junction tree. There are lots of different methods. And so what we're in some sense talking about in this variational framework are these various different trajectories between these two extremes. One of which is expectation propagation, another which is, what we saw last time, the generalized belief propagation, and more others of which we are still to see. Okay. Does that answer your question? Okay. So in expectation propagation, we can have, we sort of break the exponential family model into two pieces. We have the tractable component here and the intractable component here. Okay. And the assumption is that the base model is tractable. This is the sort of the base model, where you can think of it as essentially all of the parameters, all of the canonical parameters associated with the intractable statistics are set to 0. Right? So it's all this stuff here is set to 0, which basically means that all of the statistics are, the intractable statistics are non-existent, and so therefore you get the tractable model. And then there's another model, which is just the augmentation of the tractable model with one statistic, the ith statistic. And so the assumption here is that, when you think of it as an exponential family model, you multiply in that additional factor associated with that ith statistic, and that doesn't render the model hopelessly intractable. Like the example would be I could correspond to an edge in a graph. we talked about based on these single sort of intractable elements being added to the model, an outer bound. So basically, I think this slide actually talks about this a little bit better. So we have the mean parameter family associated with a tractable model. So a given set of pseudo-marginals, tau, is a member of the mean parameter family. Let's zoom in a little bit on this. If there exists a probability distribution such that tau is equal to the expected value with respect to that probability distribution of the tractable statistics. Okay. And then on the other hand, we have this sort of intractable mean family here. We're saying that tau and tau tilde are a member of the intractable mean parameter set if there exists a distribution such that both tau and tau tilde, remember tau tilde consists of all of the mean parameters associated with all of the intractable statistics, all of them, so over all I. And that has to be the case that when you take the expected value with respect to p of both the tractable set of statistics and the intractable set of statistics, you get back simultaneously tau and tau tilde. And what this, the question is now, L is an outer bound. And it's still basically of the same dimension as M, right? So like, for example, we can talk about tau and tau tilde existing in M. Well, tau and tau tilde might also exist in L. But what does that mean? Well, it means, first of all, that tau has to be a member of the mean parameter family of just the tractable statistics. And it's basically saying that there exists a p such that this is true. That, for example, when we take the expected value of p with respect to the tractable family and the ith intractable statistic, we get back this thing here. And this has to be true. There's a missing for all I here. This is saying for all I. Okay. So basically it means that if you're a member of, if 17.18 is true, if you're a member of the true mean parameter family, then you have to be a member of L, right? Because basically it's saying that 1p gives you all of these tau tilde super i's, right? Because you've got all of them. On the other hand, if you're a member of L, you may not be a member of M, of the 17.18, because you're only requiring there to be there could be a different p. Now, the one thing about the p has to be the case that the mean parameters for the tractable family are the same. But it could be different, and you have to be a mean parameter consistent with these tractable family statistics and also be consistent with the ith intractable one. But for these different ones, you don't have to be sort of consistent. For these different intractable ones, you don't have to be consistent across the intractable ones. Very similar to how we saw in the 3 cycle a couple of lectures ago, where we could define a mean of an edge, so it's basically a two-dimensional distribution defined on each of the edges in this 3 cycle, where if you marginalize across the edge down to each of its incident nodes, we get something that's consistent with the distribution on that node. But it's not the case that that set of means along that along those 3 edges correspond to any distribution which would give you the mean simultaneously over all statistics. So therefore, we can see that 17.17, if you're a member of L, you're therefore a member of M, but not vice versa. So L is an outer bound. And so we have this relationship here. Okay? And I wanted to say that a little bit more clearly this time. So we did say that last time, but I updated this slide a little bit. So then we can then define, since the tractable family is by definition tractable, its entropy is tractable. And since the ith augmented family is still tractable under, the assumption is that that's true, the ith augmented entropy is also tractable. So we've got this and this that's possibly that's easy to evaluate. And then the approximation to the entropy, the EP approximation to the entropy is equal to this. Okay, and so that entropy 17.14, since it consists of components, all of which are easy to compute, means that that entropy is easy to compute as well. And so therefore, we have the maximization over this outer bound of the combination of the statistics. So we have tau, which are the tractable mean parameters, and tau tilde, which are the interactable mean parameters. But we're using quantities, the entropy and the outer bound, which makes this whole thing computationally feasible. And this is essentially the strategy. This is the variational. This is the variational setup, which corresponds to the strategy that's used by expectation propagation. And also, I can't remember. I think we're going to talk about this a little bit today. So, if we have a graph, if we take the tractable family to be just the vertices of a graph, and then the intractable family to be the edges, then we get exactly the beta approximation. Okay. But on the other hand, we could do something different. Like we could take, like what we're going to talk about is tree-based EP. If we take the tractable family to be some spanning tree, and then the intractable family to be all of the edges except for the spanning tree, then we get a very different algorithm, a very different quantity. So we set this Lagrangian. So we have this total maximization process. So here's the same thing that we saw, but we have to be subject to tau being in the mean parameters. And we did this sort of funny Lagrangian where we had to duplicate the tractable family mean parameters a number of times, namely the number of times corresponding to the number of intractable statistics. Now you might say, well, why is this necessary? Because this is, first of all, this is a valid way of doing the optimization because we add constraints saying that the taus have to equal to the eta i's for all I. So it's valid. And then it turns out that that's the thing that actually allows you to connect the variational approach to the standard ways that people do message passing in EP. Okay. And then the strategy becomes the following, this moment matching procedure, where you form this sort of augmented distribution. So this is the augmented distribution associated with the ith intractable statistic. And so it basically consists of these original canonical parameters plus all but the ith Lagrange multipliers multiplied in by this tractable statistics. And then we add essentially a term, the inner product between the parameters associated with the ith intractable statistic and the ith intractable statistic itself. And then what we do there is then when we compute, I don't actually have this on the slide, but if you remember correctly that if you look at the Q distribution down here, the Q distribution by itself, as opposed to it corresponds only to this piece, where you have the parameters theta, the canonical parameters, and you're summing up all of the lambda sub L's, including the ith one. And so this would be Q, which is actually used down here for this expected value. And so what happens is the following, is that you form this distribution in equation 17.19. Then you compute these expected values of the statistics. And then what you do is you want the moments to match in some sense. You want basically in this ith augmented extended exponential family, the expected value of those statistics to match the expected value of the statistics given the under the tractable family, where what you're adjusting are the Lagrange multipliers. And those adjustments in the Lagrange multipliers, interestingly enough, when it corresponds to, say, nodes and edges of a graph, the adjustment of the Lagrange multipliers correspond precisely to message passings, just like in the beta approximation, strangely enough. But it's amazing that, again, one of these things just sort of, you do this optimization and the message passing stuff pops out. And also, by the way, it can be seen as a Kullback-Leibler divergence minimization step. Now we'll talk a little bit more about Kullback-Leibler divergence later today's lecture. But actually these mean adjustments correspond to essentially Kullback-Leibler divergence stuff. Okay, so this is a review. So remember, our overall approach, this is something that we've said many, many times here. We have the cumulate function, which is expressed as the dual of the dual. And we have that the dual is often, for the set of mean parameters that we're interested in, equal to the negative entropy. And if we had some easy access to the cumulate function, we could actually compute the probabilities that we want. But what we want to do is we approximate this and this. So I've said that many times now. And so we have these different ways of doing so now. So remember, the first way is that is the beta approximation approach, where we use as the mean parameter space the tree-based polytope, tree-based outer bound, and the beta entropy. The next way that we saw is the generalized Bilmes propagation or Kikuchi variational approximation approach, where basically we have a hypergraph-based marginal polytope, which is defined based on some hypergraph and hyperedges. And we also have an expression of the entropy, which is also based on something similar to the shattering coefficient or the overcounting number. And we essentially plug those in. And now we've got the expectation propagation approach, where again, all we're doing is we're setting the mean parameters to this EP-based outer bound, based on the tractable statistic, and the negative dual to be equal to this EP entropy. So you're starting to see a pattern here. We're just plugging in things for M and for the entropy and solving, looking at the Lagrange multipliers. And the form of the Lagrange multipliers turns out to be some form of message, which in some cases also corresponds to a Kullback-Leibler minimization step. So in some sense, if you understand this basic idea, then it's a really simple idea. We're just putting in different approximations. And then there's a lot of details associated with these different approximations. This is very, very high level now we're talking. But if you put in these different approximations, you're getting potentially vastly different tractable approximation algorithms for doing inference in graphical models. Now, you might wonder why there's all this space down here. The reason is because there's more to come. We're going to see other approximations, and they're all going to have the same approach. Okay, any question on that? I hope that if you understand anything, you understand this slide and this slide. Okay. Raise your hand if that's true. Oh, good. Everybody raised their hands. So, okay. So let's continue on with how EP corresponds to the sum product or the beta approximation. So as I said, EP generalizes the beta approximation that we saw. And we have node or vertex statistics and edge statistics. So here are the vertex statistics and here are the edge statistics. The base distribution, which consists just of the node statistic, is basically just a product of factors. So it's like an independence distribution. In fact, when we normalize this thing, since it's a product of unary potentials for each node, this distribution, under this base distribution, we're saying that all x of I is independent of x of j. So under the base distribution, that's true. So therefore, anytime we want to do inference on the base distribution, if we have a polytope associated only with the base distribution, it's basically the hypercube. And if we have an entropy associated with the base distribution, it's just a sum of singleton entropies. So and computing entropy over a singleton value is just basically summing over R values. So that's really cheap, right? Very, very, very tractable base distribution. The augmented distribution, as I said, is where you take every one of these intractable statistics corresponds to an edge. So I, in this case, remember I ranges over the set of intractable statistic. In this case, I corresponds to an edge UV for all UV in the graph. So therefore, when we refer to uppercase phi, we can just use as a superscript u and v, which is the edge corresponding to the intractable statistic that we're talking about at the moment. And so then when we're finding the augmented distribution, We augment it by one intractable statistic, the edge UV. And so we have the product over all V. And then we have that one intractable statistic. Now this is, again, a very, very simple distribution. It's certainly easy to compute. In fact, it's saying that if we look at the distribution and the independent statements associated with this distribution, we're saying that x of I is independent of xj for all ij, except for when I is equal to u and j is equal to v. So that's the only one that's not assumed to be independent. So but that's at just one edge. And so if we were to take the outer bound associated with that, well, we would get almost the hypercube, except that along one dimension there'd be some dependence, and then along two of the dimensions, u and v, and then the entropy would be a sum of entropies corresponding to the individual nodes, and one entropy corresponding to the pair uv. I think I have an expression for that. So here's the entropy of the base distribution. So like I said, it's just basically a sum of node entropies. And here's an entropy of the augmented entropy. So the entropy, it's the entropy of tau 1 through m and tau uv. And so the assumption here is that you're in the outer bound associated with the polytope where tau uv is consistent with tau u and tau v. Okay. So what that means is that if we were to look at the entropy of this joint distribution, right, where everything's independent except for tau, except for u and v, and then for that pair we have the joint distribution tau uv, the entropy therefore corresponds to the sum over all these guys that are not either u or v of the entropies. Those are, again, the singleton entropies. And then we have one entropy associated with the edge that's not independent. Okay. Well, another way of writing that is let's add and subtract the same quantity. So let's go ahead and add in all of those, the two entropies of tau u and tau v, so that we can sum over all vertices. And we sum over all vertices of the singleton entropies. And then we'll subtract them out again here. So then the whole expression then becomes this thing, which is basically something where it looks very similar to the first base model entropy, but we're adding this quantity, which is h of tau uv minus h of the singleton entropies. But that actually corresponds just to the mutual information. That's the definition of mutual information. Now, notice that this is already starting to look a lot like the EP-based entropy, right? In the EP-based entropy, what we're doing is we're not just summing over one edge. We're summing over all of the edges, and each edge has, for the entropy, a term that looks kind of like this, right? It's basically the difference between the joint and the two incident marginals. So that sort of begins to motivate that expression a little bit more. And here is that expression, in fact, expressed using not the difference of these entropies up here, but instead using the mutual information. But here it's done for all of the edges in all the intractable statistics, all of the edges in the graph, not just for one of them. So this is the full EP entropy. Now again, this is a tractable thing to compute because there's never ever an entropy that involves more than two random variables. So at worst, in terms of the number of values of the random variable, this is an R-squared prospect. Yep.
Is that plus or minus?
It's definitely plus or minus, yes. It's not divide, if that's what you're asking. No, I'm joking. It's plus. Thank you. So that's a typo. But it's fixed now, and I have to remember to fix it, so I highlighted in some color. OK, any other questions? OK, so So we have the base mean parameters, and all the base mean parameters does is basically says, okay, every sort of singleton pseudo marginal has to be a valid marginal. It has to basically, be non-negative and sum to 1, right? So the base mean parameters are very simple. It's just you live in the hypercube, right? And then the augmented mean parameter is basically almost the same thing, except it asks for you to be marginally consistent along that one edge that you're augmenting to the base statistics. So the edge in this case is UV, right? And so basically that yellow stuff there is basically the additionally required marginal constraint that defines the augmented mean parameter space. And that's also a polytope, right? And then if we consider this overall outer bound, it's basically saying that for all edges, if we take this projection, so remember now we've got pseudo-marginals associated with every unary node, which are the taus, and also pseudo-marginals associated with every edge, which is tau tilde. And then if you're saying, okay, you're one of these pseudo-marginals that live inside of L, the requirement is that at every edge you need to be locally consistent with the corresponding incident vertex marginals. But you don't need to be globally consistent. There doesn't have to be some distribution, which when you take with respect to that distribution the expected value of all the statistics, you get all of those marginals, both at the edge and the nodes. So does this remind you of anything? This reminds you of the I've already said this is the local consistency polytope, right? In this case. So it's the same thing that we saw when we saw loopy belief propagation and the beta approximation. Okay. So the base distribution Lagrange multipliers has the form of this, where we have the factors associated with every node, and then we also have these Lagrange multipliers in the base distribution. Now notice that there's a Lagrange multipliers associated with edge UV, which consists of lambda UV and lambda VU. Okay. But then when you reorganize this whole thing from 17.8 to 17.9, what we see, interestingly enough, and this is where it gets really interesting, interestingly enough, is that we're multiplying all nodes, and then we have this thing here, which is basically the potential associated, sort of the unary potential associated with that node, and then the sum over all, let's just zoom in on this so we can see it a little bit better. The sum over all neighbors of the node S, and then this Lagrange multiplier from T to S. So doesn't this remind you of, if this is the node S, and these are all the neighbors of S. Let's say that this is V1, V2, V3, and V4. So that looks a lot, surprisingly a lot like sending messages. So it's up there, up in an exponent, right? So it's the potential at S, which is this guy, and then we're summing these messages in. But if you're down out of the exponent, it would be the potential function, and we're multiplying these messages in, just like what we normally do when we're doing loopy belief propagation. And indeed, that's what happens. In fact, when we look at the expression of the marginal, that's exactly the same thing. There it is down there. Well, let's give it a special color. Let's give it a blue color. So there it is down there in blue. Okay. So that basically is the marginal, the node marginal, just like what we saw. And then if we look at the augmented edge distribution, so let's say that we have some edge L. So basically it consists of these edge these node marginals, and we have this additional augmentation, which is the augmentation associated with the edge at u and v. Okay. So what we do then in EP, this by the way, so also, I mean, it's not exactly the same as constructing the edge marginal, but it's overall the joint distribution. But if you think about essentially running the EP algorithm, what you're also going to get is something that will then give you the edge marginal as well by sending in messages corresponding to the vertices that are incident, well, I should say, the vertices that are neighbors of the two nodes that are incident to the edge that you're computing the marginal over. But the way the EP algorithm works is that we repeatedly choose an edge. So we do the following process. We repeatedly choose an edge, and then we adjust these parameters in the equation 17.8, which is, that's the equation that corresponds to the node marginal right here. So that the distributions on the nodes, u and v, match the marginals along the edges. So that's essentially sort of repeatedly marginalizing down along the edges to the corresponding nodes incident to that edge. So this is, again, the sort of marginal update procedure. This is the message passing procedure. But on the other hand, EP is much more general than this. So EP can do beta. Question?
So in the previous slide, I think the Lagrange multipliers must be UVP.
Yeah, that's a typo. I thought I had fixed that typo. Talking about here? UV. Yeah, this should be V and U, and this should be V and U, or vice versa. Yeah, that's correct. Thank you. Correct. You have good eyes, especially since even with my glasses on, I have trouble distinguishing between the two symbols for in LaTeX and between U and V. So, okay. Obviously, if all EP could do was reconstruct the beta approximation, then it wouldn't be an interesting procedure. But it can do much, much more than that. So, like, for example, we might, as I've said, the base distribution might be a tree. And what that does is it gives us this thing, and which has been, it's sort of a celebrated algorithm in approximate inference, tree structured expectation propagation. And so here, basically, we form a spanning tree. And there could be a variety of ways. So then getting back to your question, well, how do you construct this spanning tree? One way you might do it is with a Chow-Lu tree. So we didn't talk about structure learning, but what a Chow-Lu tree does, it's very simple, so I'll just briefly talk about it, since it's an important thing that everybody should probably know about. Let's say you have some graph which is not a tree. Okay? So what you do is then you have, between every pair of nodes, you can compute the mutual information. That's something that's usually possible to do based on, say, training data. So if you've got training data, then it's easy to sort of ignore all but the training data corresponding to those two nodes and compute the joint distribution just on those two nodes. And that gives you a weight. So if this is like node 1, 2, 3, 4, 5, 6, and 7, then you'd have weights associated with each one of those nodes, like, for example, weight 1, 2, and weight 1, 6, and so on and so forth, weight 2, 6. And the idea is that weight ij is equal to the mutual information between x of I and x of j. So what the Chow-Lu procedure does is it basically finds a maximum spanning tree in this weighted graph. So it finds a tree, say that would be a tree, and let's say that's the maximum spanning tree. And the reason why it's sort of, and that actually turns out, why would we find that? So that turns out if one was to if one was to sort of compute the Kullback-Leibler divergence between a tree approximating distribution, namely one that factors with respect to a tree, and the true distribution, which tree approximating distribution would have the smallest Kullback-Leibler divergence? Turns out the Chaolu tree has the best approximation amongst all exponential number of trees. And since max spanning tree is something that's easy to compute, it's just the greedy algorithm computes that exactly, it's a very, very easy way. So that's one instance in structured learning where it's polynomial time to find the best structure when the structure is a tree. And so when you choose in the place of EP a reasonable tree, tractable distribution, one that is best approximating, because that's the one you can do exact on. You're going to be doing inference, sort of exact inference on that tree. Maybe you would do a Chaolu tree. That probably would work best, or work well. But there might be other constraints. But however you choose it, you choose some tree. And so then you have this tree-based base distribution, where you've got the node potentials here, and then you have the edges only associated with the tree that you've chosen. Okay, over to the right. Now you have all these other edges that you haven't yet chosen, the edges that don't live in the tree. And so the augmented distribution, the I augmented distribution would be for every one of these edges that you haven't chosen in the tree. And obviously there's a typo there. But you would basically form a distribution where rather than setting all of the intractable parameters to 0, you sort of multiply in the factor associated with that edge. Okay. Okay, and then there's a couple of other points. I mean, so I think you can imagine there could be other substructures beside a tree. There are a couple of other points I want to sort of summarize about expectation propagation. So if it's the case, like if you form this Lagrangian, so very similar. So basically what we've been doing is sort of associating the Lagrangian and stationary points of the Lagrangian with fixed points of the belief propagation algorithm. So if you do this sort of moment matching procedure of the expectation propagation, the question is, when does it converge? What does it converge to? What's going on? Well, first of all, does there exist a fixed point of the EP-based propagation? And the answer is yes, if it's the case that the Lagrangian has at least one sort of optimum. On the other hand, there's no guarantee, very much like BP, or loopy BP, there's no guarantee that expectation propagation is in fact going to converge. So you might just run it and it might not actually converge. And this is something that I've said, you can actually derive, like we've just done, EP based on the variational framework. And we can recover the beta approximation, like we just said. And the moment matching of EP can also be viewed very much like message passing can be viewed as a strategy to compute the Lagrangian optimum. These EP-based updates can be seen as a way or a strategy to compute this Lagrangian. And as I've said also, there are many, many different algorithms, and you could think of all sorts of different structures which might be easy to compute. I mean, it's sort of interesting. Like, you might think that the tractable, even if the tractable structure is not entirely tractable, like let's say there's some large loops, you might even consider having the tractable structure, solving it with one approximation inference method, and then using that inside of EP. So you could imagine hybrid methods that are both beta EP. I don't know if anyone has done that, but there are a variety of generalizations and flexibility here. This can be done for Gaussians. And there are a lot of details that we're glossing over here. One of the things that we're going to be talking about is ways in which to sort of deal with convergence, is sort of this convexification stuff. We're going to be talking about that next week. And there hasn't really been, at least I don't think yet, hasn't been a full development of EP and the convexified variance, which is what we're going to do next week. But we'll talk about that. We'll come back to that. OK, so here's where we are. These are the variational approximations we've so far covered. The beta, the Kikuchi, and EP. OK, so the next one we're going to do is mean field. And since this is another topic, this is going to be slightly different. This is a good time to take a break. So let's take a short break, and we'll come back with mean field. So the mean field approach is sort of a different take on the variational approach, but actually it still falls within the same domain. So far what we've been doing is like we have these mean parameters in the mean parameter space, and for the most part we've been, like for example, when we do the beta approximation or when we do the EP approximation, we construct an outer bound on M. Right? So an outer bound, basically, when we're looking at the cumulant function, if everything else is being equal, like if the entropy is exact and we construct an outer bound and we take the supremum over the outer bound, then what we're going to get is an upper bound on the cumulant function. But in general, because the entropy is also approximated, we don't get a bound at all. But in the mean field approach, it's kind of interesting, because what we're going to be doing is taking an inner bound of the mean parameters, and we're not going to approximate the entropy. Although it's going to be a little bit funky, the notation, and that the notation that they use in the book and the notation that we're using is that we're going to use a different notation for the entropy, but the entropy is going to be something such that whenever we use any of the mean parameters in this inner bound, that entropy happens to be very easy to compute. So in other words, if it was the case that, since it's an inner bound, I mean, every point within this inner bound is going to be a valid point in the original mean parameter space. So they're all going to be valid mean parameters. But it's just going to be essentially a set of parameters that are easy to compute the entropy. So for those points that we're computing the entropy for, the expression for the entropy can be simplified, and so therefore we use a different notation for it, even though it's not an approximation for those points in the inner bound. And then thanks to that, since we're in some sense not approximating the entropy, and we get an inner bound, and we're taking the supremum over an inner bound, we're going to get a bound on the cumulant as well. So what kind of bound are we going to get? A lower bound, right? Because we're taking the supremum and over a smaller set. So the supremum can't be as big. Now, the inner bound is again sort of based on a tractable family. And a tractable family is going to be some family within which inference is doable cheaply. Like, for example, it could be all independence, which is sort of the traditional mean field approach, or something like a one tree, or all these things, these tractable subfamilies that we've been talking about. Although the way in which the tractable family is developed is very different than what we've done in the EP case. Now, the other problem with this, on the other hand, is that many of the approximations, while they don't give us bounds, are convex. Here we're going to get a bound, but it's not convex. So we might not get the true supremum, unfortunately. So it's sort of like whack-a-mole. Like, you can't win. Like, if you have a convex problem, but it's difficult, or you don't get a bound. But here you get a bound, but it's not convex. So what do you do? You can't have your cake and eat it too. You can't have your bound and it be convex too. Right? That's the expression. Actually, that's not true. There's a convexified form, which we're going to be talking about next time. You can have your cake and eat it too. So what is the tractable family? So we have a graph, G, and it's presumably intractable. So we find some spanning subgraphs. So remember what spanning means. Spanning, basically, if you've forgotten, just in case, means that we've got all nodes, and a subgraph means that it's a subset of the edges. Okay, and this is the notation that we're using. So F is a spanning subgraph. It's got all of the nodes, and E sub F. So E sub F is a subset of F, subset of E. The simplest example would be no edges, where it's the all-independence model. And another example would be a tree, where E sub T is a tree. There's a spanning tree. Now, it's an exponential family. And so we can sort of group together it's sort of derived in a slightly different way. Like, what we did in the EP case is we said, okay, we've got these tractable statistics and the intractable statistics. And the intractable statistics were essentially were things that we compute over. Here what we're doing is looking at the graph and taking a subgraph with respect to the graph. Now, in some sense, these things are related to each other, but here we're driving it based on the graph, and there we're driving it based on the statistics. So we can take the statistics that are associated with the family. So the statistics are the ones that obey the subfamily. So the subfamily. So these are meant to be. This is the notation. So F is the tractable subfamily, and then I of F is basically the subset of the statistics that obey all of the independence properties specified in that subfamily. Now, the canonical parameter space, as a result of this, gets smaller. So here's the original canonical parameter space, which is omega. And here's this new canonical parameter space, which is omega sub f. Now, the dimensionality of this canonical parameter space in the mean field approach doesn't get small, although actually that's not officially true. We will talk about instances where we're looking at a subspace of the canonical parameter space. But in this case, in equation 17.14, the dimensionality is staying the same. So we're still in the same, in some sense, ambient space of the original canonical parameter space. But what we're doing is the following. We're sort of taking the, you're in this subfamily if, first of all, if you're in the original canonical parameter space, but all of the canonical parameters associated with the statistics that don't obey the family are set to 0. So one thing I could ask you is, like, why set to 0? Why is that the canonical family? Why is that the canonical family parameter space in a higher dimensional, in the original ambient space, the higher dimensional ambient space? But why is that the sort of subset of the canonical parameters in the ambient space corresponding to the subfamily? And why is it setting it to 0? Because setting it to 0, does anyone know?
That's when you don't have edges.
Setting it to 0 turns off the edge, essentially. Because if it was not 0, like let's say you're two random variables. That's exactly right. So you have two random variables connected by an edge. And now suddenly you're saying, OK, it's a subfamily, so remove that edge. Now we've got one statistic associated with that edge. If the statistic had a parameter that was non-zero, it would basically say, oh, there can be a dependence between these things. And so we're not abiding by the rules specified by the subfamily if it's the case that the parameters, the canonical parameters associated with the statistics matching the edges that we've removed are non-zero. So we have to therefore set them to 0 to respect the subfamily. And that's I just said all of that down there. This is all this stuff. OK. Now, right, so this is a Markov random field with potential functions for nodes and edges. For each edge, we have this potential function for that edge. And then we have a subfamily which turns off all the edges, basically says, here's the canonical parameter space for subfamily F naught, where F naught is basically everything independent. It's basically turning off the canonical parameters associated with every edge. Turning off meaning setting to 0. So that's just an example of what we saw. And the resulting family is just going to essentially give us a set of independent. It's going to give us a distribution of independent random variables. Okay. So that's pretty trivial. Here's a tree example. What we're doing here is basically all canonical parameters that are associated with edges not in the tree, we're setting to 0. I think this is pretty straightforward. But if we were to do that, what we get then is a tree-dependent distribution, which can be written in this form, as we saw. So this is a standard way of writing a tree. OK, any questions about that, these examples? OK. So the mean parameter space corresponds to traditionally, or what we've been talking about so far, and we're going to use this notation. It's basically the mean parameter space associated with G under the G subfamily, which, since G is the same, it's basically identical to the notation that we were talking about before. It's associated with a graph G and a set of statistics phi, and it basically consists of the mean parameters associated with G and all of those statistics. So we're sort of in that ambient space dimension. But now what we're going to do is we're going to use this notation because we're sort of in the dimensionality of the same statistic space. We need to have both G here and F, which is the subfamily. So it's basically saying that we have G and phi. So we're still associating with the graph. We're still in a dimension. The dimensionality of the space of the mean parameter space that we're talking about is still based on phi, which is all of the statistics, but we're only really talking about the ones associated with a subfamily. And that basically defines us a mean, which again is an R to the D. So D, remember, is the dimensionality of the full statistic space. But it's basically saying that it has to be a mean that's obtained by taking the expected value associated with a probability distribution with parameters theta, where theta lives in the canonical subfamily space. Remember, theta is the one where we've set all of the canonical parameters to 0 that don't abide by the properties in the subfamily F. Okay. So if this is a little bit confusing, basically all we're doing is we're just going back here, well, into this case here. We're saying we're defining this is the canonical family space, and we're defining the mean parameters associated with that. Here we are, doing that here. So therefore, we get this following property, that we get the that since it's the case that any parameter theta that lives within omega sub f, which is a subset of omega, remember, so omega sub f are all of the ones that have the canonical parameters associated outside that don't abide by the f set to 0, then any mean parameter that we have here would also live inside of here too. Right? So we have an inner approximation, an inner bound approximation of the mean parameter space. Okay, so this is just saying this because of this property. Does that make sense? I mean, again, if you just look at this bit here, this is for any theta in the subset of the canonical parameter space. So therefore, this would also live, theta would also live inside of just full-on omega. But if we just took some omega where the canonical parameter associated with a missing edge that's in, say, E but not in F was non-zero, then we would no longer be in this space. And so therefore, the reverse relationship obviously doesn't hold. So this is just some shorthand notation that the book uses and that we're using as well, where we don't have to keep mentioning phi. The important thing is we can refer to both G and F, or just G here. And the assumption is, again, that when we're not mentioning phi, when we're talking about F, in the canonical parameter space, those canonical parameters are 0. So one thing to note is that, so we've got this now inner bound. So what does an inner bound mean? So we've got the mean parameter space, which might look like this, and we've got an inner bound. So that means that every mean parameter that we are considering optimizing over is a true mean parameter. It's not one of these pseudo-marginals. It's actually a real marginal. But we're just not getting all of the marginals. We're missing these marginals. So if we optimize over just the orange part, and we're maximizing, we're taking the supremum, we're going to get something that's smaller, assuming the entropy is not approximated. Now, the other thing to note, of course, is that, I mean, any mean parameter any mean parameter mu is just automatically going to yield a lower bound on the accumulate function. And the equality holds only if we've got this dual coupled thing. I mean, this is in some sense an obvious theorem, right? Because just if you look at the definition of the accumulate function, it's the supremum over all mu of the inner product of mu. I mean, here's the proof. I mean, it's the supremum here over all mu of the inner product of mu and theta and the dual. But on the other hand, it's also interesting to show that you can prove this using Jensen's inequality. And this is a traditional proof that was used in mean field theory, and rather than convex duality. And basically, what you do is you let Q be any distribution that satisfies the moment matching. In fact, it doesn't even need to be an exponential family model. So any distribution that satisfies mu is equal to the expected value with respect to Q of the phis. Okay? So then when we go to compute the log Q, the cumulant function, this is the cumulant function, then what we can do is we multiply and divide by Q. And so that's presumably just 1. That is 1, or, and we can just simplify and just to say that Q is a non-negative is a positive distribution, if you're worried about that. Or you can deal with it with limiting arguments if you want to be very precise, or with the measure nu, because the measure is still sitting there. And but in any event, the point is that Q cancels out. But now you can think of this as sort of like this probability Q of x multiplied by this quantity here in red. And so it's sort of like it's basically like a log of an expected value of some quantity. Right? This is the quantity in red. Okay? And since the log is a concave function, and we use Jensen's inequality, right? So here's the two extreme points, and say here's log of the expected value. And then we can use Jensen's inequality and say, well, let's take the expected value of the log, which would be then this point here, which is going to be a lower bound. So it's the expected value of the log. And then the log, as soon as we take the log, then we use the fact that it's an exponential family model. So it's an expected value now of the log. And the log is basically the inner product, theta times phi minus the log of Q. Okay. Now that whole thing basically evaluates to theta times the expected value with respect to Q of phi. And now we've got this entropy quantity in here. Right? It's expected value of log Q with respect to Q negated. But on the other hand, we're also using this moment matching restriction. So P is any distribution that satisfies this. So we can substitute this with mu here. And so we finally, at last, get the final quantity. Okay, so what does this mean then? So we optimize over all Q. So remember, if we optimize Q over all M, so remember, Q, I should mention, it has to be the case still that we're respecting this thing. So we consider the Q that maximizes it over all M, and what we're going to get is equality. Right? So another equality meaning this is equal to this. But on the other hand, and this is where the mean field lower bound comes from, if we optimize over a subset, any subset of M, like for example, the one that comes about from the tractable family, namely this one down here, then what we're going to get is a lower bound on the accumulating function. So it's not like, for example, necessarily we're going to use one point mu, but we're going to optimize over a subset. OK. Now, here's the trick, like I said. Normally, it's the case that this dual, A star, which, if we want to get the accumulate function, we take the dual of the dual, right? So the one problem is that, of course, the polytope is hard. The other problem is that the dual of the dual, or that the dual itself is hard. So we can't take the dual of the dual without actually having the dual. And what we've been doing is we said, OK, well, the dual is usually like the entropy, the negative entropy, and we approximate the entropy in some way. And that's the thing that usually screws up our bound. OK. In the mean field approach, however, is that we're going to take this inner bound on the polytope, namely this thing, such that the entropy is easy to compute. And so the goal of mean field is to do this maximization. So we're taking, and here's I mean, we're going to say this in an example, but just to give you an intuition, it's like how is it possible that the dual of the dual would be easy to compute? So suppose it's the case that we're taking an inner bound, and let's say that the inner bound, namely this thing that I just highlighted in pink, corresponds only to the mean parameters corresponding to fully factorized distributions, namely everything's independent. Okay, so these are marginals and everything's independent, right? So that basically means that any distribution along an edge really is just a product distribution of the corresponding marginals on the nodes incident to that edge, right? So now you've got this entropic quantity, and the entropic quantity might be this very complicated thing, but suddenly everything becomes a product distribution. And so the entropy essentially just becomes the regular sum of the singleton entropies, sum of the unary entropies. And it's easy to compute. So the entropy is not an approximation. It just so happens that for this region of the mean parameter space, it's easy to compute. So I think this is what this says. So we're doing this maximization, but we're maximizing or taking this supremum, whatever, over this restricted family down here. And where this dual, this is where it might be a little bit confusing because the book uses a different notation, but if you were to write out the entropy, it would be a different form of the entropy, but it's only a different form of the entropy because you know something about the distribution. And for that particular distribution, this different algebraic form of the entropy is not an approximation. And so that's why they use this notation. And that basically becomes the mean field approach. And I think that is what this says. Right, so this is sort of saying here again. It's not an approximation. Rather, it's just easy to compute. OK, so remember, fondly recall your days in your youthful, when you're youthful indiscretion, and you would come to this class back in lecture 13, and you encountered this slide, and you were happy because at that point things still made a little bit of sense, right? So we talked about the relationship between the cumulant and its dual, right? So we said, OK, well, this is stuff that we've, of course, all be saying, that we've got the dual here, which is equal to this, and then we've got a representation of the cumulant function in terms of the dual of the dual. And we said that equality in both of these things happen in the moment matching conditions. Right? Moment matching conditions is what essentially gives you this in terms of equality. Like if we were to remove this supremum and plugged in a particular value of u, or we were to remove the supremum here and plugged in a particular value of theta, those values that reach equality would happen here at these moment matching conditions. Then, of course, all this stuff over here is just relates it to the entropy. So yes, I did not run a spell checker. So the conjugate dual optimizations, these optimizations, namely this optimization here and this optimization here, interestingly enough, can be seen as a Kullback-Leibler divergence minimization process. And in particular, the mean field, once we see this as a Kullback-Leibler divergence minimization problem, the mean field approach is going to be seen as finding the best tractable family distribution that approximates the more complex distribution. And doing this potentially repeatedly. So how do we show that this is a Kullback-Leibler divergence, first of all? Okay, so what we're going to do is we're going to see how this stuff, equations 7.3 and 7.4, 17.3 and 17.4, corresponds to that. Okay, so we've got two distributions, P and Q. The Kullback-Leibler divergence is basically this. It's a divergence measure. It's not a metric. It's not a distance function. It basically is something that's 0 when the two distributions are 0, and everywhere else it's non-negative. In fact, it's 0 if and only if the two distributions are identical, and everywhere else it's positive. And then there's an integral form. There's a summation form if you've got discrete sets. Everybody's familiar with this. Yep. Question.
Wasn't that Kullback-Leibler divergence coming out in the proof technique you used itself, because you had a Q of x that you kind of multiplied and divided, and then you brought the log inside, and that was exactly a negative Kullback.
Yeah, we're gonna make this a little bit more explicit here in the mean field approach. But yeah, we already talked about this implicitly. Now, in the case when P and Q are exponential family forms with the same set of statistics, then we're going to see some interesting interpretations of this, and also in terms of a Bregman divergence, which is a generalization of Kullback-Leibler divergence. So we're going to actually just take notational shortcuts. So basically, since we know when we're in an exponential family form, we can parameterize an exponential family either with the canonical parameters or the mean parameters. We can actually talk, for example, about Kullback-Leibler divergences between, say, theta 1 and theta 2, and what we really mean are the distributions associated with theta 1 and theta 2. Or we could talk about the Kullback-Leibler divergence between mean parameter 1 and mean parameter 2, which really corresponds to the distributions that use those mean parameters that respect those. Or these sort of like hybrid approaches where you can say the Kullback-Leibler divergence between mean 1 and theta 2. So that shouldn't cause confusion. Basically, all we're talking about are the distributions associated with either the canonical or the mean parameters. Okay, so let's take two canonical parameters. And the corresponding Kullback-Leibler interpretation. And the corresponding mean parameter. So if we look at the Kullback-Leibler divergence, and we're taking the expected value with respect to the first one of the log of the distributions with respect to the first, and the ratio is of the first to the second. Now we can actually write this once we expand, because basically the log of an exponential distribution family using the notation we're talking about is really just the inner product minus the cumulant function. So what we've got then is really just the difference between these two cumulant functions minus this inner product, where it's the inner product between the mean parameters at 1 and the difference between the canonical parameters. Okay, and now you can actually look at this in the following quite interesting way. We can sort of think of it as this cumulant function minus this whole quantity here. And that quantity here, in some sense, can be seen as a linear approximation to the cumulant function that's tight at value theta 1, and everywhere else it's a lower bound, because the cumulant function is basically, it's convex. And so let me just write something here. So you can think of this as some function. Let's just call this h of theta 2. And it's theta 1. So the idea is that h of theta 1 is equal to a of theta 1. And h of theta 1 theta is greater than or equal to a of theta. So it's tight at theta 1, and everywhere else it's an upper bound. And it's a linear function. And it has slope. What is the slope, or the gradient, equaling mu1. And in fact, we can interpret it this way, and we can interpret the Kullback-Leibler divergence as the difference between this linear approximation at theta 1 and the true cumulant. So here we see this is the true cumulant, this blue line, which I'm highlighting in yellow. And here's that function that we just saw. This would be equal to h theta 1 of theta. Okay, and it's this red line. And then you've got 2 points. We've got theta 1 and theta 2. And this is the value of the cumulant theta 1, the value of cumulant theta 2. And the Kullback-Leibler divergence then is just this gap. Okay, this gap between the convex and the affine lower bound. Okay, so that is essentially the way in which you often define a Bregman divergence more generally. But here we're seeing the Kullback-Leibler divergence in this fashion. Now, where we're going to see how these supremum operations correspond to a Kullback-Leibler minimization problem is by, I think it can best be seen by looking at sort of the hybrid form. So first of all, here's the expression for the dual. And as we said before, the dual is lower bounded by this expression for any canonical parameter theta. So because remember, we're optimizing over all theta, and so for any fixed theta, that's going to be a lower bound. So what we're going to do then is write the Kullback-Leibler divergence in this sort of interesting way. So here's the Kullback-Leibler, and there's the expression that we just saw, plotted in the previous plot. And let's take out the cumulant evaluated at theta 2 minus this bit. And this is basically just corresponding to theta 1, sorry, mu 1 and theta 2. And what we're left with is that part and this part. Okay. But so now we can then we take this and copy it down here. But then this expression because we're assuming the moment matching conditions, namely that theta 1, or sorry, that mu 1 is equal to the expected value with respect to the distribution at theta 1 of the statistics, mu 1 and theta 1 are moment matched pairs. And moment matched pairs means that those are the pairs that actually achieve the supremum up here. And so therefore this expression, which I was going to highlight here, this is highlighted in green, this expression here corresponds exactly to just the dual. So we have this really interesting expression for the dual. Let me just highlight the whole expression for the dual. It's a hybrid dual, but it's still a dual. So basically it's like the, a really interesting expression for the Kullback-Leibler divergence, the hybrid Kullback-Leibler divergence, which is the cumulant at theta 2 minus the inner product plus the dual at mu 1. Okay, so what do we do with this? So then if we look at the variational expression for the cumulant, namely the supremum in equation 13.7, by the way, that is equation 13.7. That's the 7th equation from lecture 13. This is called LaTeX magic. How does this happen? So if you went back, and actually if it really worked, then you would tap on it and it would jump you into LaTeX, into lecture 13, but that's not working yet, unfortunately. So that expression for the cumulant can be seen as the following. So it's taking the infimum. It's like if you, I mean, the way you see this is like get rid of the supremum for a minute, subtract this from this, and then we've got an expression that looks a lot like this here. But in order to achieve the supremum, that basically means that, the difference between this bit over here and this bit over here has to be 0. So the infimum, and we're optimizing over the same thing. And so since in the supremum in equation 13.7 we optimized over mu, we also take the infimum over mu. And so basically that equation, then sort of summarizing what I just said, this equation 13.7, taking the supremum, is the same thing as taking the infimum over this expression. But look at this. We've got this expression here and then this expression here. So these two blue expressions turn out to be exactly the Kullback-Leibler divergence, which is here. So therefore, we're taking the infimum over mu of the Kullback-Leibler divergence. Now, what if it was the case in the mean field approach? So just computing the cumulant is a Kullback-Leibler divergence minimization problem. And if we were to take an inner bound on the mean parameters associated with a tractable subfamily of models, then that would be like a projection in some sense. It's basically saying, OK, well, find me from amongst this tractable family of models, like all independents or a tree or whatever you want, find me the one that's closest to the distribution theta, or the exponential family model associated with canonical parameters theta. We should all be smiling now, because this is a great connection. Right, so I said this. Solving the mean field variational problem, which is this thing here. And by the way, so in this expression, we're saying that these are identical because whenever the means are in the subfamily, we have these two things are identical. In general, it's not true. But because we're only considering the mean parameters in the subfamily, those two things are identical. Then solving that is basically identical to a Kullback-Leibler divergence minimization problem subject to being a mean parameter associated with a tractable family. So this is what I already said. Kullback-Leibler divergence over nice families. And the nice family thing is going to mean that we can actually do this minimization. Right? OK, so here's the Ising model example. We have statistics associated, as everyone should be very well clear about at this point. We have statistics associated with the nodes and with the edges. And in this particular case, if we're looking at the mean parameter space, we've got the means that corresponding to the vertices, and then any of the edges, since it's a tractable subfamily without any of the edges, namely here, it must be the case that for any of the edges, the mean parameter at edge st corresponds to the product of the mean parameters at s and at t. That's the subfamily. So anytime we're talking about an edge joint distribution, it's really a product distribution, because under these mean parameters, everything's independent. We can still talk about them, and they can still live within this higher dimensional mean parameter space, but they have this factorization property. And therefore, thanks to that factorization property, the entropy is super simple to compute, which is great. And even more simply, since everything's independent, the inner bound is just this hypercube. And so the variational lower bound problem is the following. We maximize over this of this quantity. We have the original guys here. Now, one thing I should mention is that if you look at this middle one, notice that we still have a parameter associated with st, but the mean parameters are factored, mu s mu t. And then also here, this becomes an entropy. Now this is, this is just the form in the mean parameter space. This is the form of the mean parameters when we're considering this this mean parameter space where everything is assumed to be independent. Okay, so this is this constraint. I think I've already said this. This is the n-dimensional hypercube. But this problem is non-convex. And the way you optimize this, however, there's actually a nice way of optimizing it. It's non-convex when you think of it jointly, but you can do coordinate ascents. And interestingly enough, when you do coordinate ascent, with respect to each coordinate, holding all the other coordinates fixed, this actually does turn out to be a concave problem, thankfully. So each coordinate optimization is concave. So and this is where suddenly the standard mean field approach that you saw early on when people were talking about mean field pops out. So you do coordinate descent, and the process that you optimize this objective is you choose some point S, and you optimize the mean parameter mu sub S, so vertex S, and you fix all the other mean parameters. And you take derivative of that objective that we saw that we're trying to maximize over. And what you get is the following update rule. We get we take the canonical parameter S, we sum over all neighbors, we squash it with a sigmoid function, and then it gives a new mean parameter. So it's kind of like taking the neighbors, taking your canonical parameter at the current node, taking all your neighbors, summing them together, squashing the result by a sigmoid, and you get a new mean parameter. This is in the binary case, of course. And then you just repeatedly do this. It's basically like a message passing thing, but basically each node collects from its neighbors. Each node collects from its neighbors, and you just sort of dance around the graph, collecting from your neighbors, and then squashing the result with a sigmoid so that you're still a distribution, and therefore still within the mean parameter space. That is the classic mean field update. And what we derived it from, again, from this variational principle. So again, I think that the evidence stands to reason that the variational approach is very, very powerful. So one more bit about the lack of convexity. So the book actually has an example where I'm not going to go into the details of this, but basically what you can do is you can construct in an example where we're taking sort of a spin version of the model where the random variables take on +1 and -1. The relationship between the random variables and the probabilities is represented here. So the mean parameter, actually, if you add 1 to it and divide by 2, then you get the probability of it being +1. And if you subtract 1, if you do 1/2 of 1 minus mu, then you get the probability of it being -1. And so you have an expression for the entropy. And you have the thing that you're trying to optimize in the mean field objective is this. And so you're trying to optimize for the current corresponding mu's. And here's a particular simplified form of a submodel parameterized by Q. And what the book just shows is that for various different values of Q, like for some values of Q, if you set Q to be equal to 1/2, then you get a nice concave form, and you can optimize it. This is jointly in mu1 and mu2. But on the other hand, for some values of Q, like for example 0.01, which is closer to 0, you get something which is clearly not concave. And so therefore it's not a convex problem. Okay, so what we're going to do is next time, on Monday, we're going to talk about structured mean field, which is essentially a way of doing mean field, but for tractable families being things other than just an all-independence model. And I think it's an important example, especially for those people interested in time series, because that was the first example, I think, of this when this was done was, I think, in the late 90s, which was done for factorial HMMs. And so factorial HMMs are essentially a bunch of coupled HMMs. And the idea is that you can use structured mean field to sort of have your tractable structure be a bunch of uncoupled HMMs. And the uncoupled HMMs, and you sort of repeatedly go from sort of solving independently each of these uncoupled HMMs and then doing these mean field updates at each time. And it's a really nice example. So, okay. Are there any questions? Do you wish you had questions? Would anyone like to hear a joke?
Don't delay it.
So don't delay it. Actually, I don't have a joke. I have to disappoint you. I can tell you a joke. I can tell you a joke online. So this is a joke that my